Session, the answer is no. So that's why this is blank. But I'll just put up a few, hopefully provocative comments, and then we can open that for discussion. So I really like to tie what we heard this morning into the question about what is the relevance here for quiescence and quenching. And one statement would be that the stellar feedback cannot quench any galaxies. Sort of think most people will agree with that at least at a massive end. Okay, we don't think stellar feedback is a source of quenching. We know that at the low mass end, supernova feedback can temporarily quench a galaxy by just blowing out the gas. Whether that will be called quenching depends on your definition, right? So if you take the definition that I proposed at the very first day, where quenching is the process of actually moving from the blue cloud into the red sequence, there is a time scale associated with that. And if the time scale in which you have your repetitive burst on which the gas comes back and you get your next burst is basically shorter than the quenching time, then stellar feedback will never quench. Okay? It will just temporarily shut down star formation, but that wouldn't make my definition of quenching. I would argue even stronger that stellar feedback cannot preserve quiescence ever. Okay? So it can temporarily maybe blow out some gas, but it eventually will come back. So it's not a proper maintenance mode. I think the ultimate problem lies in the fact that you try to quench star formation with star formation, which is like a, is doomed to fail, right? So, but the more interesting question, I think we heard a lot about that, is that what is the role of the older populations? Okay, so can AGB stars, luminous X-ray binaries, stellar remnants like accreting white dwarfs, to what extent can they actually play an important role in the entire business of quenching and quiescence? And I think they're definitely an important source of radiation. I think they're definitely important in somehow controlling the rate at which something forms stars. It's unclear to me whether they are important for actually quenching or maintaining quiescence. So I'd love to hear people's view on that. And then finally, okay, always the problem is, do we have to worry about stellar population uncertainties? To what extent do they make important contributions to uncertainties that people like who run simulations have to worry about, or who make some analytical models? Is this a dominant source? Is this a subdominant source? And I think definitely when you talk about things like if we believe these older populations are an important contributor to galaxy formation as a whole, I mean, I certainly think this is an issue. But I'd love to hear anyone's view on that.
Can I just address this last point, not on a point of view of quenching and quiescence, but rather in a comparison with data. As we saw Merritt yesterday put up plots showing stellar age versus some parameter, and we saw them again today. Mm-hmm. Remember that when people measure stellar populations, in general, they're measuring an SSP. Mm-hmm. Even the more complicated situations, you're only getting very average quantities for entire populations if you're doing more sophisticated population analysis. And we know that basically if you get an age of between 2 and 5 gigayears, you're only measuring basically what's happened in the last 0 to 3 gigayears at best, depending on which method you're using. And most methods really only around 1 gigayear, basically telling us how much star formation happened in the last gigayear to 2 gigayears. For all optical methods, basically, this is true. For UV methods, it's basically true from half a gigayear to 1 gigayear. So you're not actually measuring the age of the population in any sensible way. You're not measuring when the stars formed. You're only saying how much stars formed recently, on average. So please...
You're talking about, but that's a statement about integrated light properties.
Integrated
light stellar populations.
I think if we have M31, the Milky Way, dwarf galaxies in the local group, and hopefully when we get to the 30 to 40 meter telescope area, we'll get out to Virgo. We'll be able to do a bit better than that. But at the moment, please, if you're comparing to Sloan, and you're using people's ages, don't use them as an indicator of when the stars formed. I don't know how many times I need to say this to people, but please don't do that, because you're not learning anything about a sequence of star formation. You're learning about what happened recently and what happened a long time ago.
It's a birth rate.
It's a birth rate.
Or a specific star formation rate averaged over 1 or 2 years.
I think you can still get around that a little bit. So if you stack instead on the ratio of the lines, like where you expect it to lie, and then look at the colors of the population, then you might be able to say something interesting about that for that particular case.
modular
I think
dust.
if you ask the question carefully, I think that
Yes.
I would agree with you. So,
No,
Also, the last
It-
part, I would say,
you have to be
we
very
shouldn't
careful.
worry about cell population uncertainties until we try to take the most optimistic case in terms of energy injected and hardness of photons, etc. See if that works in terms of either maintenance or quenching. And if that works, then go back and say, okay, are we actually correct here? Because even if the most optimistic case, this doesn't work, then you don't have a problem. That would be my practical approach, and I don't have to do it. Third point, quenching starvation is due to fail. I agree, totally. That's why I think it's really a question, do we get enough energy in whatever form from those populations that, well, I call it, have already been paid for, and will actually return energy until eternity, some almost constant over time, some decreasing over time. Because that's the old problem, with maintaining a quenched state, also with AGN, right? We need to have a model which sort of allows a little bit of matter flowing back, but we might want to do that episonically, or you want to do that at a very low rate.
which is, that's exactly why I was impressed by Marat's talk when he showed the contribution of these low mass X-ray binaries and the creating white dwarfs, and it to me looked like, whoa, are we missing something very important here? I mean, the creating white dwarfs maybe it's a red herring, but low mass X-ray binaries, they are detected, we know they're there, and maybe X-rays do contribute significantly. Do they contribute significantly to the energy budgets that we were talking about for quenching?
Just in case I made too strong a statement, and Moran as well, there'll still be some population of the creating white dwarfs, and they can't exactly be ignored if you're used to higher ionization emission lines and things like that.
But that contribution that he
It's
showed
not-
on the
it's not
SED,
this huge world.
it cannot be,
Yeah.
right. Great.
Well, I don't want to anticipate too much on my talk this afternoon, but it's going to be exactly with this problem. Most of it will be for not quenching transformation, but regulating transformation, but can also be applied to the issue of quenching transformation for a long time using X-ray radiation, and not in the sense of transferring energy to the rest of the medium, but more like acting on the cooling rate of the gas, because the first, most important ingredient to keep things quenched is that the gas doesn't cool in the first place. That's not really transferring energy, it's more like changing the cooling physics. And I'm going to show this afternoon that X-ray radiation, especially the one that is used by low mass X-ray binaries or whatever, is very important in science cooling in the first place.
Looking forward to that. So,
Yeah, so why can't star formation, quench star formation, or keep an early type galaxy clean of gas by driving stellar wind? The stellar mass loss rate, the change in the stellar mass loss rate over time is about the same as the supernova heating rate over time. So if you do it once, you can do it for a long time. So why do you say it's doomed to fail?
because I think, well, it's largely because simulations basically predict, just kidding, that they don't. But I mean, if you go, well, I think there's an interesting question. If you go and look at a quenched galaxy, what I would call a galaxy that lies on the red sequence, and you look at what its specific star formation rates are, we're talking about 10 to the minus 11 or something. Is such a star formation rate and the corresponding supernova energy injection rate sufficient to keep gas from coming in?
Well,
Energetically,
I think
maybe, but in practice, whether you can actually couple that energy in an efficient way, I haven't seen anyone being able to
You guys
tap
are
into that energy.
cross purposes, right? Because I think the quenching star formation with star formation is doomed to fail is just accounting for the actual energy input from the young stars. Whereas I think Joel is trying to emphasize that in principle you can get rid of the AGB mass loss by energizing it with the
That's
supernova 1A.
No, the bug's there, right?
Right.
So if it's an older population, if you want to quench star formation with really making young stars, I don't think that's gonna work. I
Oh,
think
with
that's-
young stars, okay, yeah.
But then the question was, Nate, whether the overall populations, whether they can.
Even with
give
young
you-
stars, in principle, it can be done. I don't think the simulations can say that. I think I could make a simulation that can do that. The problem is that the galaxy formation is assumed to get more efficient towards 10 to the 10 solar masses, which basically means you have to make the feedback less efficient getting to that mass. Then it somehow would have to suddenly become more efficient to quench behind that, which is difficult to do with one process. So it's difficult to explain. But if you just, I mean, I think there is actually enough freedom in the models. If you didn't care about the low mass evolution, you only want to quench the high mass, you could do that. You just have there's quite a lot of energy and momentum from the young stars.
Energy-wise, I agree with you, but whether you can actually make it grow. Phil, you want to say
So
something?
if you actually, if you force, I mean, if you take the observed specific star formation rates, there's more energy in the old stellar populations than in the young ones for ellipticals.
Yeah.
And I think the other point is, it's pretty obvious that quenching star formation is doomed to fail, because if you go to the lowest mass galaxies where stellar feedback should be the most important, those are the systems where, when they're centrals, every single one in the universe forms stars. Right? So it's obvious that irrespective of what the simulation says, nature does not do that.
That's what I was saying. It's the low mass one that's important. If you didn't
Right.
have the low mass, then there's no argument against it.
Yeah, but we do, because we're trying to understand nature.
That was my point.
With the all cell populations, I mean, what we're relying on here is numbers, because they're all lower luminosity. Star formation, they're all lower luminosity than AGN. So my question is, and my belief is, that these things will act very strongly locally, but it's very hard to get this energy much, far out into the hail. So definitely, these things will be very strong on regulating star formation within the central galaxies. But if you want to prevent cooling at large scales, you need to get energy from these stars out.
But that's, gate fractions can be really high.
That's the key. You need to escape out, so is there strong X-ray or winds from these things escaping out? And I don't know, has people shown these, or?
Well, if you go to different type systems, you model it, and you calculate gate fractions there pretty high.
The luminosity is not going to do anything at large scale.
No, exactly, that is the question. You can get it out, but how is it going to happen? So, Frank, on your second point, how do you find stellar feedback in the second line? I mean, so you don't mean stellar feedback in terms of
that-
stars?
Early still.
Yes,
Young
it-
star.
Young stars again.
Okay.
So that was an intro to the second statement that quenching star formation. But stellar feedback, I mean, we heard Phil's comments. Phil's comment basically leading towards the conclusion that, preserving quiescence basically requires an AGN. He tried everything, except he didn't try X-ray contributions. But
I mean, we could say
Yeah,
AGN,
it has-
but
it has-
it requires another source of energy, right? We cannot maybe narrow ourselves to.
But is there another source of energy that is related to stars that we can identify that might be important to include in your simulation?
I think we should consider that it's not just the amount of energy, it's also how and the density of these things. And there's one important aspect we didn't discuss yet, is that quench galaxies are very compact, while star-forming galaxies are very extended. So if you put the same amount of X-ray photons from low mass gray binaries or massive binaries, but in a much smaller radius, then the density of photons, density of energy, whatever it is much larger. And so the motivation why quench things are actually compact in the first place is because the energy, or whatever source you want to put in, the density is higher also of the photons.
The outer parts, elliptical, so very low.
Yeah, but where the old stars are, that thing is much more compact than a star forming this.
Well, I want to, actually on that, comment, part of the problem, I didn't get to get into this level of detail, but we've seen this and many other people have, is you want to invoke stars or some of these other processes, the energy is getting put in the wrong place, right? The cooling flow is not happening inside the central kiloparsec of the galaxy. You need a way to get energy out, and that's actually a real challenge. I mean, that's why people like radio jets, because we see them punch way out into the halo to radii comparable to the radii you actually need to do the heating at, to do the real work. Now, we don't know how to actually distribute that energy around in the halo there, but you need something, you know, if it's going to be
I mean-
stars, you need something that gets way out of the center.
But there is one thing that I never see people talk about. It's the fact that if you look at a cluster and you look at a BCG, the total mass of the intercluster light is about 3 times the mass of the stars in the BCG. Okay, and those stars do extend out right about over the entire radial extent where you're interested in actually doing the heating. So if you can get that old stellar population to put in enough heat and whatever, there is a possibility of doing it.
I think those are two separate issues, because you can still have gas cooling, and we see there's a lot of gas into this quench galaxy, but you have to avoid that gas turns into stars. And there's a lot of gas there. It's just this warm. It's
But-
not in molecular form.
It doesn't cool down to anything basically below about 1/3 imperial temperature. That's what, but again, that's the claims that you see a lot from the cooling club
There's a
people.
misunderstanding here also from Phil's comment. So when people do this balancing of heating cooling, the starting point is the observed density distribution clusters, which is actually completely different if you didn't have feedback to begin with. So to get that density distribution, you must have already ejected a huge amount of low entropy gas or heated it at the earlier stages. And that's, if you look at the groups, these progenitors of these objects, they have low gas fractions within R500. So the gas certainly needs to be moved even before that. And the maintenance problem is a lot easier because of that history.
Yeah, I completely agree. So it may be that, for example, some of the mechanisms that I talked about, you know, if something else had happened and moved around a lot more low energy gas, and this is a good quantitative question, I don't know yet from our simulations what our answer would be, but it's a good question. You know, if we had something else move a lot of low entropy gas out, would then these other mechanisms be sufficient, for example?
One final question before lunch. Yes. Sorry, I can't hear you.
Like the bubbles at least in the systems that we see that have lots of cool gas and lots of negative gas as well, they are moving this gas largely around these systems.
That's not so clear to me. Seeing some of the people here were saying they trigger condensation. Also in groups of galaxies, you need to have the gas fraction low out to R500, which is hard to do with buoyancy.
So you need a seed to trigger the condensation. So even if you're doing condensation, it's not coming straight from hot gas, because it's going to discuss it. So you need a seed. It could be a bit of a...
The buoyancy itself cannot move gas, cannot reduce the gas fraction, it can mix those. So it would have to be the shock heating from the jets, not the buoyancy.
Well, if you have a field, it's different.
Yeah.
You displace the gas. If I fill this room full of a low-density X-ray gas, I displace the gas. Physically displace it.
The low density gas rises up, but it doesn't, I mean, doesn't reduce the gas fraction overall permanently.
If you keep doing it, it does.
You would have to do it everywhere all the time.
Well, we see generations and generations of and some of these systems...
No, you have to have bubble essentially everywhere all the time.
I mean, so Marcello showed the simulation of jets. It's really hard to cover 100% of the volume. You can only cover a small fraction of it. The splendid volume where the gas will happily cool 80% of objects. So that's why bubbles, in principle, you can do it, but it's hard to get 100%
And you
volume
need
coverage.
to do it at the time when the galaxies were growing, when this peak of the star formation efficiency, when the light core fusion rates are high.
So
that
you
can-
have to do it now.
Yeah, it doesn't, but that's maintenance.
That's the whole point. And the rates involved are like the early phases, so it shows the problem.
Well, the rate's a lot lower because of this ejection that happened earlier.
Yeah.
So somehow we translated from stellar feedback into AGN feedback, which is not allowed, and therefore I suggest we break for lunch and we reconvene at 2 o'clock.
So wait.
Whoa.